Welcome to Brain Vision.
Okay, so in this question, we have an aluminum rod. The length of the rod is L equals 1.60 meters. And we're told that the speed of sound in aluminum is V is equal to 5,100 meters per second. This rod is clamped in the middle, and it's stroked with a rosin-coated cloth to create a sound wave in it. And the sound waves are longitudinal, but that's not really important to the concept of the problem. But in part A, we're asked to find what the fundamental frequency of this sound wave is. So it is important to note that the rod is clamped in the middle because that means that there can't be vibrations in the middle of the rod. And because the waves are longitudinal, it does help imagine that the antinodes at either end, we know that there are going to be antinodes at both ends of the rod because they're not fixed in any way at those ends, so they're free to vibrate. Since it's longitudinal, we can kind of imagine the aluminum rod lengthening and shortening with the vibrations at the end. But in the middle, it is clamped down, so it can't move, which means that there has to be a node in the middle and then antinodes at either end. So if we do kind of a wave representation of this, we're going to have antinodes at either end with one node in the middle. So this will be our fundamental of the wave. And so if we look at this, we can see that the wavelength is going to be equal to 2 times L, because we go from one antinode to the opposite antinode. In order to get a full wavelength, we have to return from the opposite antinode to the full antinode. So the length of the rod is half the wavelength, therefore the wavelength is twice the length of the rod. So then we can say that the fundamental frequency is going to be equal to the velocity of the wave divided by the wavelength, which will be V divided by 2L. So we're given V, we're given L, we can go ahead and calculate this out. So F is going to be equal to 5,100 divided by 2 times 1.60. And so our frequency becomes, if you calculate this out, you should get 1.59 kilohertz for our fundamental frequency. So that's our answer for part A. Then in part B, we're supposed to figure out what kind of frequencies, what kind of harmonics can be set up with this arrangement. And the important part here is that because it's clamped in the middle and free to vibrate at both ends, there have to be antinodes at both ends, and there has to be a node halfway in the middle. So in order to create another frequency, a new harmonic on it, we'd have to have a vibration pattern that has antinodes at both ends and a node in the middle. If we try to do the second harmonic, the second possible standing wave setup, we'd have to add a second node. We'd have to add a second node into the length of the rod, which would give us a standing wave pattern like this. This doesn't work though, so while we have antinodes at both ends, we don't have a node in the middle. We have to have a node in the middle here. So we can't have n equals 2 be one of the possible harmonics. So if we go to n equals 3, we have to add a third node in, which would create a standing wave pattern like this. Which this works out because we have antinodes at both ends, and then we have the node here in the middle. So n equals 3 works. And if you do sketches for n equals 4 and n equals 5, you'll find similar things, where n equals 4, you can set that up with both antinodes at either end, but the node won't be present in the middle, and we need to have a node in the middle. But if you do 5, you'll have antinodes at both ends, but you will still have that node in the middle. So we know that n equals 1, n equals 3, n equals 5, etc. Can be set up with this clamp in the middle, but 2, 4, 6, 8, etc. can't. So only the odd numbered harmonics are possible with this setup. So the answer for part B is odd numbered. And then we move to part C. Part C is the same as part A. We're trying to find the fundamental frequency, but this time we change the rod to a copper one, where the speed of sound in copper is equal to 3,560 meters per second. So we have the exact same calculation as in part A, we just switched this out for our V. So F is still equal to V over 2L, but V equals 3,560 now, so we just plop that into our numerator. And then in the denominator, we still have 2 times 1.60 meters. If you calculate that, you should get a fundamental frequency of 1.11 kilohertz. And that's our answer for part C, and we are all done with this problem.